Ionic solids. Ionic solids are made up of metallic ions bound to non-metallic ions. If the electronegativity difference between two elements is greater than 1.7, they will form an ionic bond. An array of ionically bonded ions forms an ionic solid. A salt crystal is an example of an ionic solid. Here's your sodium atom, here's your chlorine atom. They ionize, so you have sodium plus, chlorine minus, and notice how the size of the atoms changes. They attract each other, and here's your ionic solid. The negatively charged ions, or anions, and the positively charged ions, cations, in an ionic crystal lattice are arranged in a systematic three-dimensional array. Attractive forces between the anions and cations are maximized. Repulsive forces between like charges are minimized. So in a simple crystal lattice, anions are surrounded by cations, and cations are surrounded by anions. Ionic compounds have consistent ratios of ions. The formula unit of an ionic compound has the same ratio as the crystal lattice. The formula unit for magnesium chloride is right here, NJCTL, and the ratio of magnesium to chlorine would be 1 to 2. The crystal lattice maintains the same ratio. Ionic bonds have greater bond energy than other types of bonds. The attraction between oppositely charged ions in the ionic solids is extremely strong. The crystal lattice holds on to its ions. The valence electrons of ionic solids are tightly bound to their nuclei, unlike those of metals. These strong attractions are the basis of the observed properties of ionic solids. We can think of the ions in ionic solids as being held in place by their oppositely charged neighbors. As a result, ionic solids tend to retain their solid array. This lattice structure gives rise to the properties of the ionic solids. They are typically brittle, poor conductors, have high melting points, have high boiling points, and they dissolve in and change the properties of polar solvents. Ionic solids are brittle, not malleable. When struck by an external force here, ions may shift in their lattice structure. If like charges come into contact with like charges, they will repel, and the crystal will shatter or crack. Ionic solids are poor conductors of electricity because their electrons are tightly bound to their nuclei. Electric current requires the flow of electrons. Ionic liquids conduct electricity because the ions are free to move, creating an electric current in the presence of a voltage. Ionic solids have high melting temperatures and high boiling points. The tightly bound ions are reluctant to separate and move. A lot of heat is required to melt ionic solids and boil ionic liquids. Ionic compounds tend to be solids at room temperature. Ionic solids readily dissolve in polar solvents such as water. For example, if we add sodium chloride, that's salt right over here, to water, the sodium and chloride ions dissociate and go into solution. Here's a negative chlorine, here's a positive sodium. The ions tend to leave the lattice as shells of water molecules form around the ions, ushering them away from the solid. The ions in solution are referred to as electrolytes. Electrolytes impart new properties to the solution. Electrolytes are ions in solution. The presence of electrolytes allows the solution to conduct electricity. Even though the ionic solid that contributed the ions is an insulator, once dissolved, the ions can flow, creating an electric current when a voltage is applied. This explains why magnesium chloride is spread on roads to melt ice. The magnesium and chloride ions decrease the likelihood that water will stay in a solid crystal because the water molecules are attracted to the ions. Therefore, the water remains liquid at lower temperatures. When sketching ionic solids, it's good to have an idea about the size of the ions. The large difference in the sizes of atoms are reduced somewhat when comparing the sizes of their ions. The metals and semimetals get much smaller as they lose electrons to become cations, while the nonmetals get much larger as they gain electrons to become anions. Ideal gases don't form ions, so they're not included in these trends. This is shown in the chart on the next page, which is worth reviewing for a few minutes, but not memorizing. The chart shows the size of each atom and the size of its typical ion. The ion size is shown in dark gray. So here for lithium, that's the smaller piece. And it's smaller than the atom on the left of the table, but larger on the right side. So here's sulfur 2-. The ion is much bigger than the atom. So on the right side, the ion gets bigger. On the left side, the ion gets smaller. So you can pause the video here and just check out some of your favorite elements and see what happens to them. Sketch the solid structure of potassium bromide. You can use the chart on the previous slides where it shows the various sizes of the ions. So the bromide ion is larger than the potassium ion. The arrangement must show the 1-to-1 ratio of the atoms, and the positive ions must be surrounded by negative ions, and the negative ions must be surrounded by positive ions. So that's what we have right here. Sketch the solid structure of cesium fluoride. You'll need to consult the periodic table that showed the sizes of the various ions, and we find that the cesium +1 is larger than the fluoride -1 ion. So the arrangement must show the 1-to-1 ratio of the ions, the positive ions must be surrounded by the negative ones, and the negative ions must be surrounded by the positive ions.